In this video, I want to talk about three vector spaces that we can associate with any matrix. I'll define these vector spaces by looking at an example and saying what these spaces are. I'll talk a little bit about why we care about these spaces, although admittedly, it takes working with them to see how useful they are. And then finally, I'll introduce some nice properties of these spaces, in particular, how their dimensions relate to each other. So we have in front of us a matrix A. It's a 4 by 3 matrix with 4 rows and 3 columns. And the first space that I want to associate with A is what's known as the row space of A. So the row space of A is just the span of the rows of A. Now notice I've written these as column vectors because that's what we're doing in this course. But the rows of A, if you look back up here, we can see it all on the same screen. The rows of A are 1, 0, 3, which is our first vector in this list. 0, 1, -4, the second vector, and so forth. So the row space is the span of the rows. In this case, there's 4 of them. And because each row has 3 entries, the row space of A is a subspace of R3. Up next, you might guess, is the column space of the matrix, which is the span of the columns of the matrix. So in this case, we have 3 columns, each with 4 entries. The first column is 1, 0, 2, 1. And so that's the first vector in my list. And the other 2 vectors are the other 2 columns of the matrix. So we have 3 columns. So it's a span of 3 vectors is our column space. And each vector has 4 entries. So the column space of A is a subspace of R4. All right, a third space that I want to associate with this matrix requires a little more definition. It's the null space of the matrix. And this is the set of solutions to the linear system that you solve by setting up an augmented matrix with A on the left and the 0 vector on the right. So in this case, this is A, the left-hand side, and this is the 0 vector. So the null space is the set of solutions, and in this case, it's a subspace of R3. Because an augmented matrix with this sort of form, we have each column corresponds to a variable. We have 3 variables. Any solution is going to be a vector with 3 numbers, 1 for each variable. So the null space of the matrix is a subspace of R3. We have these 3 subspaces. Why do we care about these spaces? And again, this is just an initial look at why we care about these spaces. It's one of those things that it's hard to explain why these spaces matter without understanding how to use them. And so there's a bit of a chicken or egg situation where you, to some extent, just have to kind of suspend disbelief, believe me that these are useful spaces to think about. And as we move on and see more and more applications where these spaces show up, you'll be more and more convinced that they're useful. But just really quickly, we've already used the null space of A a lot. Homogeneous systems show up everywhere. For example, when we're trying to determine if a set of vectors is linearly independent, what we're really doing is solving a homogeneous linear system to see if there is a non-trivial combination of those vectors that adds up to the 0 vector. That's one example. We'll see them throughout the course, for instance, finding eigenvalues of matrices, which shows up in tons of applications. The null space is going to be really important to us. The column space we've also actually used, although indirectly, and this is requires a bit of thought. But if you think of this augmented matrix, we have A on the left and some vector on the right. If we want to know whether we're going to get a solution to this, if you think of this instead of as an augmented matrix, or instead of as a linear system, but as a single system of a vector equation, this vector equation is saying or asking whether the vector v is in the column space of A. Or in other words, a vector is in the column space of A if this linear system is a linear system with solutions. So we've already kind of worked with the column space, although we haven't had to use that terminology. And in applications, we'll see that thinking about which vectors actually have solutions can be really useful. One of the first places we'll see this, the real power of this, is when we do regression, where we're trying to take real world data and model it with a function that doesn't quite exactly fit it. And we'll have a situation where we end up with linear systems that don't have solutions, and we need to ask ourselves, okay, it doesn't have any solutions, but what sorts of vectors would there be solutions for? Or in other words, what is the column space of the matrix we're working with? So the column space of the matrix will become important to us. The row space is actually the hardest to justify at this point, and so I want to look at a picture. So the row space is what's known as the orthogonal complement to the null space of A. And I'll draw a picture here. Let's scroll so that it hopefully shows up reasonably. So for our matrix A, the one we're working with, this is a picture of the row space. So the row space, as we said, is a subspace of R3. It's the span of 4 vectors, but it turns out that the vectors aren't linearly independent. And well, of course they aren't, right? There's too many, but there's actually a lot of dependencies, and it's only a 2-dimensional subspace of R3. It's this plane. And I'll also draw in the null space of the matrix in blue. And what you can see is that this blue line is perpendicular to this red plane. Another way of saying this is that the red plane is the set of all vectors that are perpendicular to everything on the blue line. And we'll introduce this terminology later in the course, but vectors being perpendicular or orthogonal to each other is an important property that shows up in many applications, one of them being the one I just mentioned, linear regression. So I know that that probably wasn't a full justification of why these are useful, but hopefully you'll be convinced throughout the course that we actually are studying these for a reason. The final thing I want to talk about is the dimensions of these spaces. This is one of the places in linear algebra where things work out, in some sense, unreasonably well. So the first statement about dimensions of these spaces is that for any matrix A, the dimension of the column space ends up being the same as the dimension of the row space. And this is surprising, I think. The first thing to point out is that they're not even necessarily subspaces of the same Rn, right? In our example, the column space of the matrix was a subspace of R4, and the row space is a subspace of R3. They have the same dimension, right? I just told you that the row space has dimension 2. We looked at that picture. That means the column space has dimension 2. We'll later see why this is true, but for now, just accept it as a fact. This seems like an important quantity, the dimension of the column space, which is the same as the dimension of the row space, so we'll call this the rank of a matrix A. The rank of a matrix is just the dimension of the column space, which is the same as the dimension of the row space. The null space is not going to have the same dimension in general as the row and column space. We just saw this, right? In our example of A, the null space has dimension 1, but we still want to give it a name because it will be useful. And so we'll call this the nullity of a matrix. So the nullity of a matrix is the dimension of the null space. Tying this all together, when we look at our picture here, if I flip back, we have this 2-dimensional row space and this 1-dimensional null space. Dimension of the row space is the rank, dimension of the null space is the nullity. And they add up to the total dimension of R3, the space they live inside. This is not a coincidence. So this is what's known as the rank nullity theorem. The rank of a matrix plus the nullity of the matrix is always equal to the number of columns of the matrix. In our example, the rank of the matrix was 2. We had a row space of dimension 2. The nullity was 1, null space of dimension 1, and the matrix had 3 columns. So this is always true, which again is a somewhat astounding fact that things work out this nicely. So all of these facts about dimension, what we'll actually see is that, I just introduced these spaces. We haven't even started working with them. And in a later video, I'll talk about how we figure out bases for these spaces. That is, if they're important, and we want to work with them, we should figure out how to find a basis for each space. And the process of finding bases for row space, column space, and null space, in doing so, we'll actually see why all of these statements here are true. That is, we'll see why the column space and the row space have the same dimension, and we'll also see why the rank plus the nullity is always the number of columns of the matrix. All right, so hopefully I've convinced you, at least to some extent, that these spaces are useful or interesting or something like that. And again, in the later video, we'll see how we can start working with these spaces and find bases for them.